Hi, and welcome to this second video in the series on integration. And in the last video we looked at the basic mechanics of integration, how you physically do it, and we came across this issue of the constant of integration, and we looked at things called indefinite integrals. And in this one we're going to take it a step further and look at something called particular solutions, which is how we can use that constant of integration. So what we're going to do is look at integrating gradients to get back to a specific function, and that's all hopefully going to make sense as we go through the video. So here we go. Let's start off back at basics and say what we talked about last time, which is that when we differentiate, we know that the constant term disappears. So if I've got this curve here, y equals x squared plus 3x plus 4, and I want to find the gradient function, dy dx, there it is, it becomes 2x plus 3. And if I took a different function, this one's x squared plus 3x minus 5, and I differentiated, what do you get? You get the same gradient function. And there's another one, again it's plus 12 on the end, but again the plus 12 disappears. So all three of these curves, despite being different curves, have exactly the same gradient function. And that's happening essentially because they're parallel. But what it means is that if I started off, did this to the round, if I started off with a function like this, a gradient function, reversing this particular function would get me back to a family of curves, essentially an infinite set of curves, because I don't know what the number on the end would be. So for example, if I've got this gradient function here, so here we've got the gradient function 3x squared plus 6x plus 2, and I do some integrating, add 1 to the power, divide by the new power, that's what we get. There's my constant of integration that you saw in the last video. And we might get a curve that looks like that, it's a cubic, and we might say, okay, that would be the curve I'd get if I had a value of c that was 0. Or it might be, I had that curve, which would have a value of c if c was 6. Again, it's just the same curve, just kind of shifted upwards. Or I might get that one, with in that case c would be minus 4. And because from what I've got here, I don't know what the number on the end is, I don't know the value of this constant, what I get is essentially a family of curves. And I could have drawn, let's say, an infinite number of different curves that all have exactly the same gradient function. All of these curves have this gradient function. That's the key idea that we need to make sure that we're understanding here. So the question is, well, if I'm given a gradient function, how do I know essentially which curve it's come from? How do I get back to, as the question says, our original curve? And to do that, essentially what I need to do is I need to know a particular point on the curve. And if I know a particular point, I'll be able to figure out exactly which curve I've been working with. So there we go. So here's our gradient function. And let's say the curve that we're dealing with, we know a point on the curve is 2, 18. So we've got a coordinate that's on the curve, and this curve here is one of these family here. We just as yet don't know which one. So what we've got is our equation of the curve, and there's the plus c on the end, because that's the thing we're trying to figure out. And we know that this curve here has got this equation for some value of c. And hopefully you've already clocked that what I'm going to do is take the information here, 218, and just plug it into the equation. So when we've got y equals 18, we've got x equals 2, we get that. And so what we've got now is the whole thing just with c as being our only variable, so I've just got to do a bit of working out now. And clearly we can see that c is minus 6. And there we go, we know that this curve here goes to there at minus 6, and we know it's got the equation x cubed plus 3x squared plus 2x minus 6. So let's have a look now at another example. So here we've got the gradient function, a slightly more scary looking one. So, and we're told we've got a curve c that's going to pass through the point 410. So we need to find the equation of c. So there's my gradient function. First thing I'm going to do is get that tidied up so it's in a form that I can integrate. So hopefully you can see that we're going to end up with this. So we've got 3x squared divided by 2x. That gives us that term there. X to the power half. Sorry, again. Yeah, x square root of x is x to the power half divided by x gives us x to the minus half. Do the integrating. There's the new power divided by 2. Add 1 to the power half divided by the new power half. That just becomes 1, so it disappears. And there's my plus c on the end. I know I've gone through that fairly quickly, but hopefully you can look at that and you can see where it's all coming from. So now what I've got to do is plug in my values of my coordinates. So let's chuck those in. So we end up with that. And so now just a bit of tidying up. 4 to the power half, square root of 4, that bit's just going to be 2. And tidy it all up. There we go. And we end up with c equals minus 4. So what we've got now finally is the equation of my curve. There it is, y equals 3x squared over 4 plus x to the power half plus 4. Moving on again, okay, so we've got a kind of more practical example, and you're going to see this appearing in your mechanics studies when you get onto it, but it still might pop up as a contextual problem within the pure section. So let's just have a little look at what's going on here. So we've got a child, there he is, throwing the ball off the cliff, and we're told that the vertical speed of the ball, so just the speed in the vertical direction, is a function of time, so how long it's taken since he threw the ball. And we're told that we've got, essentially, our gradient function is 8 minus 2t, where t is the time in seconds after the ball was thrown. And what we've got to do, the question says, is given some information here, work out the height of the cliff. So, this is going to come up in your mechanics. I'm going to briefly go through it again. Hopefully it might be something you're already aware of. Velocity, we can say, is change in displacement over change in time, which is ds dt. And so it's the differential of the displacement function, and so it's a kind of differentiate function of time. And let's say again, you're going to go into that in more detail in your mechanics, but that's essentially what's happening. So in order to get back to displacement, our displacement function, because that's what we've got information about here, what we've got to do is integrate our function. And the integrator will give an expression for displacement above sea level in terms of t. So we're going to get back to this thing here. So first job is to do the integrating. So there's our function. Integrate that function. We've got 8t minus t squared. So we'll obviously add 1 to the power, divide by the new power. You can see what's happening there. And there's the plus c that we're going to deal with. And it's at this point we're going to use the information that we're given, because what we've got here is our function in terms of time. And we're told when t equals 4, the ball is 36 meters above sea level. So let's take that information exactly the same way as we saw on the previous slide, plug it in, so we've got that expression there, and that allows us to find c, so we've got c equals 20. So there it is, there's our function in terms of time, and that's the thing that tells us the height of the ball above sea level at any given time. Right, so we've got that. The question is asking us for the height of the cliff. So we can figure out the height of the cliff, because in this particular case, the height of the cliff is going to be the displacement of the ball when t equals 0, because this whole thing is done in terms of time after the ball has been thrown. So all we've got to do is say, well, when t equals 0, our function becomes 20 plus 8 times 0 minus 0 squared. So you can see clearly that the height of the cliff is 20 meters tall. So in this particular function, our constant, this 20, this thing here, is just kind of given by the height of the cliff.